Imagine you're a secret agent traversing through enemy territory and you come across a bomb. Now you don't know if this bomb is defective or still active and you want to figure it out. Now this is no ordinary bomb. It's an Elitzur-Vaidman bomb, otherwise known as a photo-detecting bomb. It's designed so that the bomb will detonate when a photon is sent through the bomb and hits a sensor in the middle of the bomb. So how do you test to see whether this bomb is active or not without blowing yourself up? It seems like you should only have two options, right? You send a photon into the bomb. If it explodes, then it works. If it doesn't explode, it doesn't work, but that ruins the whole point because the only way to know that the bomb works is by exploding it. Luckily, we live in a world where quantum mechanics exists. Quantum mechanics describes some of the more seemingly bizarre phenomena that we see in nature that aren't necessarily explained by classical physics. You may be familiar with the notion that light exhibits both properties of a particle and properties of a wave, depending on the situation. We can use this dual nature of light as an essential tool in figuring out if our bomb is active or not. In order to do this, we'll use something called a Mach-Zehnder interferometer, developed by two scientists in the 1890s. This device relies on mirrors and the ability to reflect and transmit light rays through something called a beam splitter. So how does this work? So when a beam of light approaches a Mach-Zehnder interferometer, first it will come in contact with a beam splitter. This will reflect half of the incoming light and transmit the other half of the incoming light, thus splitting the beam into two parts. Each of those two new beams of light will then reflect off of their associated mirror and then head towards a second beam splitter, which will again serve to reflect and transmit light. So here's where things get kind of weird. You may be familiar with the fact that waves exhibit constructive and destructive interference when they're interacting with one another. For instance, if two waves are heading towards one another, if their crests line up, they'll exhibit constructive interference. But if they're misaligned, then they'll exhibit destructive interference and break each other down into just a flat line where there's no wave present at all. Going back to the Mach-Zehnder interferometer now, it turns out that when the two light beams reconnect in the second beam splitter, they'll completely destructively interfere in the downwards direction and completely constructively interfere in the upwards direction. And thus, if we place two light detectors on the upwards direction and the downwards direction, only the top light detector will receive any light. So if we're breaking down the possible outcomes, there's a 100% probability that all of the light from the original source will end up at the top light detector, and there's a 0% chance that any of the light from the original source will end up at the bottom light detector. So what if we switch things up? And instead of just having the Mach-Zehnder interferometer as is, we insert a cement block after the first beam splitter. This block will absorb all incoming light, which means that after half of the light beam gets transmitted through the first beam splitter and the other half gets reflected, the half going downwards will be absorbed into the block and won't make it through the rest of the interferometer. The top beam, however, will continue on its merry way, reflecting on the mirror and then heading back towards the second beam splitter. Now at the second beam splitter, there's no other light ray that will cause destructive or constructive interference. Thus, the beam splitter will work as you would expect, and half of the incoming light ray will go up, the other half will go down, and thus, if we're looking at possible outcomes, it turns out that a quarter of the original light will end up at the top light detector, a quarter will also end up at the bottom light detector, and the remaining half of the original light was absorbed into the cement block. So what's strange about this is that when we block some of the light path, we actually end up with more light at the bottom light detector than we originally had, because of the wave-like nature of these light particles. So how does this relate to our bomb? Let's say, instead of a cement block, we inserted our bomb into the path of the light ray. If the bomb is defective, meaning the sensor doesn't work and the light ray doesn't trigger an explosion, the light ray will pass straight through in the exact same way as our original situation. The two beams will split apart, come back together, and then at the second beam splitter, constructive and destructive interference will cause no light to hit the bottom light detector and 100% of the light to hit the top light detector. Thus, if our bomb is defective, we expect to see all of the original light end up at the top light detector. However, here's where it gets really counterintuitive. If our bomb is working, then it will work just like the cement block in our second situation, because it will serve as an obstacle intersecting the path of the light on the bottom half of the interferometer. Thus, when we originally send a light ray into the first beam splitter, again, half will go upwards, being transmitted, and the other half will go downwards and intersect the bomb. Yes, unfortunately, in this situation, the bomb will explode. However, the transmitted light that goes onto the top half of the interferometer will continue on its way, reflecting on the top mirror and heading back down to the second beam splitter. Since in this situation, the bomb is an obstacle, so no light comes from the bottom half of the interferometer, we see the exact same thing we saw in the case of the cement block. A quarter of the original light will head upwards towards the first detector, and the other quarter of the original light will head downwards into the bottom light detector. So to summarize, if the bomb is working and we send one photon into the interferometer, half the time it will trigger the bomb to explode. A quarter of the time, the photon will end up at the top light detector, and the other quarter of the time, it will end up at the bottom light detector, something we did not see when the bomb was defective. This shows the beauty of quantum mechanics. The photon does not interact with the bomb, yet it somehow knows that the bomb works and that the bomb is blocking the path of the light. That's what's amazing about quantum mechanics. In classical physics, you usually have those yes or no situations of either the bomb explodes or it doesn't. But in quantum mechanics, we see particles like light with both particle and wave properties, making it so that they don't react according to yes or no situations, but they react according to different probabilities of given outcomes. So in classical physics, if you wanted to figure out if the bomb was defective or not, you'd have to send a photon in. If it explodes, it's working. If it doesn't explode, then it's obviously defective. In quantum mechanics, 25% of the time, if the bomb is working, it will cause light to head towards the bottom light detector. Quantum mechanics gets into all the weird properties of photons and electrons that display characteristics that we'd never expect from classical mechanics. And when studying the field, you'll run into lots of situations like this, where the photon and the bomb never interact, yet the photon somehow knows that the bomb is there, and it changes the possible outcomes for the photon. Now you might be saying to yourself, there's still a 50% chance of detonating the bomb. And yes, those aren't great odds, but there are ways to refine the interferometer so that it's less likely the bomb will explode, and it's more likely that the particle will end up at the bottom light detector. So there you go. This is how you figure out if the bomb works or not without blowing it up. Just make sure to stand pretty far away in case it goes.